let's get started. Nick's leading us again today, talking more about QA systems. So want to take it away, Nick?
Yeah, sure. All right, so today we'll talk through some of the options for a retrieval component of a QA system. And just for a little, to pull out a little, I think we're going to work on QA systems specifically for a few more kind of topics and posts. We want to come out with a couple more tutorials that'll give you better state-of-the-art systems that you can kind of plug in for question answering, as well as just more content on kind of the components required, what they do, and which ones might be best. So you kind of get a cookbook full of question answering components and NLP components for you to understand and know how to apply in the future. So that said, today we're just going to look at a couple of the options for retrieval, and this is essentially information retrieval that is a sort of classic task in NLP. But today this is a little more focused on question answering. So if you recall from maybe the last talk or the last post, one of the stages in a modern question answering system is that we have a query and we have a kind of database against which we look, and we have some kind of reader. And the retrieval component is just there to take our query and look through the database of text we have in this example and find the best options. And then we use those best options combined with the query, and we try to figure out from there with our reader model what the best possible answer is. So it's really, this retrieval option is really sort of evidence gathering that we then feed into a model that's designed to specifically answer a question. So yeah, here are a couple of the options, and some of this is kind of historical and basic, like these term-based ones are just, they've been around a long time and they're very simple and effective. And some of the other ones are newer, and quite a few are pulled from more like very recent systems that are trying to build a sort of optimal question answering system, and they use some of these techniques. So efficient QA was a competition at the end of last year at NeurIPS, and basically it was a Google sponsored competition, and their team participated and a few others participated. It was sort of asking people to, given some question and a Wikipedia index, give us the answer. It's really a very basic kind of trivia, but instead of being one model, these teams could kind of create their own sort of ensemble model. And what they ended up using and what ended up being top results used some of these retrieval, specifically these dense retrieval options. So some of these are very kind of cutting edge, but it's more about understanding the kind of techniques and sort of little hacks and ideas that these teams are using.
What was the name of that competition again?
Efficient QA, cool. All one word. And it has, yeah, it's got its own website. I can link this later. It has its own website. And there's also a kind of write-up paper on archive afterwards where the people who ran the competition and many of their participants kind of shared, what worked the best, what was the makeup of the optimal systems, what are the insights we can take away. And I share some of those in the blog post we wrote at the beginning of the year on a sort of review of a few interesting results at NeurIPS. So if you check out that blog post, you can see some of the summary of that efficient QA paper and competition. So it's a good place to look if you're interested in modern question answering systems. All right, onward. So term-based systems are very kind of traditional information retrieval, and the idea here is always stick with the example of question answering. If I have some question and I want to retrieve the best the best candidate passages that are related to this question, well, let's just match the words I find in this question with the words I find in this database of passages. So bag of words is specifically just that. TF-IDF sort of takes into account the frequency of words. I'm not going to go into great detail on these because there's a million write-ups, and they can do better justice than I can. But TF-IDF sort of understands, well, the word the occurs a lot because it sees it within a corpus a lot. So it shouldn't be that important if your question has the word the, and a number of these other passages have the word the. It's not really an informative way. So it sort of finds the most infrequent relative to the corpus it's looking at, finds those words, which are kind of the most informative for helping you pick out different versions. And in kind of in production settings, or in maybe just more advanced settings, you'll see BM25, and there's a few variations of BM25, but essentially they're all kind of souped up versions of TF-IDF. So one of them differences accounting for document length, which can be somewhat of a problem in TF-IDF if you have a very short document. Term frequencies get kind of skewed, as opposed to if everything is a nice 1,000 words long. TF-IDF is much more interpretable, but if you have a short document, the frequency gets a little weird. And term frequency saturation, it just has these kind of, if you look at BM25, it's literally an equation, and it's got some kind of smoothing functions added onto the traditional TF-IDF equation just to make things a little more intuitive for information retrieval. So the strength of all of these, is that you don't need to train anything. They work kind of pretty well out of the box. But a sort of main problem that most people have seen, and I've seen had to work around, is that if your question contains the word, piano or something like that, there's no ability for these term-based retrievers to find synonyms or related words. So maybe your question is about pianos, but there's no way to tell the system that it should also look for passages that have the word instrument in them, or music, or pianoforte or harpsichord, or any of these kind of things. So there's no synonyms, and there's no kind of the strength that neural systems have where they understand what words are related. It sort of lacks that, and that could be a big or not big problem depending on your use case.
So a couple things. There's a simpler retrieval system too, right? Which is like Elasticsearch, where you're just sort of like keyword matching, right? Mm-hmm. Would that be like, does that kind of belong? It's like another layer here that's like keyword matching, something like that. And then these are like vector based, right? So you're generating a vector representation of each document, and then using like cosine similarity and k-nearest neighbor search to. Mm-hmm. And I guess that gives you like a score too, right? Because you get a cosine similarity.
Yeah, typically these do some kind of maximum inner product, which is just the cosine similarity. Sort of.
Yeah. Okay.
Yeah, it's true. I haven't used the Elasticsearch much, so I'm not very familiar with it. But it's sort of like a plug-in, strictly keyword search engine.
Right. Yeah. It's just like an indexing machine, right? It like, locates. It knows the position of every word in every document, and lets you do Boolean searches and things like that.
Does it rank results? Sorry?
I'm sorry, does it work on phrases then, or is it just really keyword?
Yeah, you can do, you can put your terms in quotes, right, and it'll match a sequence of words.
And then you can do cosine similarity, I guess, between the vectors. Is that the idea?
Let's see. Are we talking about so with Elasticsearch? There's no vectors involved. It's just it's an index really.
Okay. Got it. Thanks.
Do you know if Elasticsearch or how it ranks results? Is it just number of hits?
Yeah, I feel like there is some sort of like scoring mechanism there, but I forget how it works.
Yeah, there must be some kind of ranking thing, but
Yeah.
yeah. So yeah, there's another option. I haven't played with it, but it is a in the haystack, deep set haystack question answering kind of ecosystem. That's one of the plugin options you can use to sort through documents.
Yeah.
So.
And then the other thing I was thinking about is like, I know we have a tutorial on LSI where basically you just dang it, what's that called? You're in PCA to forgetting the terminology. But it basically
dimensionality reduction for. I have also not even thought about LSI for probably a good 2 years.
Right. Yeah. So you do end up with so much shorter vector, and then it handles synonyms because it's like making linear combinations of the components of the bag of word or TF-IDF vectors. But I imagine the models further down this list are much newer and more powerful than LSI even. So
yeah, I mean certainly trade-offs of forget how fast LSI is, but certainly BM25 is very fast versus a lot of these involve some kind of transformer model encoding. So you do take a hit on speed, certainly. So for many applications, TF-IDF or BM25 or maybe LSI, these are not necessarily bad options. Okay, so the next sort of category of retrievers is dense retrievers, and this is sometimes called neural information retrieval. And here we are, we're essentially trying to encode vectors that we can use against our query. And these are neural vectors, so they've run through any kind of multi-layer perceptron, any kind of model. And they have some sort of dense, uninterpretable, but very rich encoding of the passages or the question. So DPR is I think Facebook came out with this a year or so ago, and it's sort of the one component of their model, Retrieval Augmented Generation. But essentially, we are running our question and our passages through two separate BERT encoders. Each one encodes, so one is responsible for encoding the question. One encodes all reference passages, and you take the dot product of the CLS token of each of these, and this gives you the sort of the similarity. And this whole model is trained end to end. This diagram is not. It's for the next model, so don't pay attention to the diagram yet. So essentially, it's two. We're feeding this through, and then at the end, we use this similarity as a kind of metric. It's a loss function, and we backprop. And so as we go through, as we go through, we're training each model to try and generate encodings that end up being good at, how to put this, they're basically good for similarity matching, because the loss function is, if they are in fact similar, then we want them to, if they are in fact similar, then we want them to have a high similarity score, and if they're not, we want them to have a low similarity score. So it's a labeled exercise. It's a supervised training exercise. And so some of the data set for this would look like one question and then the corresponding passage from which this question can be answered, and that would kind of be a gold label. So when you feed those through, you want at the end, our label is 1 or positive. We want those to have a very high similarity score. And if you feed through the question and an unrelated passage for which there's no way to get the answer, you want that to have a low similarity score. So eventually these two encoding models try and approximate how I can generate this such that at the end it'll be able to produce reliable similarity scores. And I'll say that 2 BERT encoders are small. I think they're they might just be 2 layers each. They're not full-on enormous BERT encoders, but they do have the same kind of architecture. And this kind of DPR serves as a blueprint for, and is itself borrowing a blueprint from a lot of neural information retrieval. The idea is you either encode both the question and the passages, or separately through 2 different models. And these models, they don't have to be BERT encoders. They can be any kind of neural model. And then we want to train them to have a good similarity score at the end. So this is the blueprint for most of these dense neural information retrieval systems. And a lot of the submissions in something like Efficient QA, they're literally just running these through custom models they built. And if you look at DPR code, it's really simple, just a couple encoders, a very simple loss function, and you train it. Okay, so that's kind of if you understand one of these systems, this is a good one to understand because it's sort of very basic and it gets used a lot. It's also in Hugging Face, so as of not that long ago, it's in Hugging Face, so you can use it. It might not be the best in every task, but it's certainly up there usually. So if there's one you want to focus on and try from the neural branch of retrievers, then DPR is a good candidate. And the rest of these are essentially kind of variations, and they have different ideas about different problems, but they're sort of the kind of addition or variation maybe you would come up with if you had a problem for which DPR wasn't quite doing its job or could be improved. So they're just kind of more ideas for retrieval that might be interesting for your application or just interesting in general. So we'll just run through a few of these. MDR is multi-hop dense retrieval. And this multi-hop is a good term to know for question answering. It refers to the case where the answer to a question depends on combining information from 2 distinct sources. So this can be a real problem, and in some question answering tasks, this is the problem, where instead of asking you about, in this diagram, instead of asking you about Judy Lewis's birthday, which can just be retrieved from one passage, we ask the question, what was the nickname of Judy Lewis's father? So there's no single passage in here that is possible that we can answer that question with. You need to basically combine information from 2 different sources, and this is referred to as multi-hop. And so this is a retriever designed to facilitate that. So it's very similar to DPR. See, we encode the question. We use it to retrieve the best candidate passage similar to DPR. And then, sort of in the meat here, we take that result and we add it to the original question, and then we use that encoded sort of new vector to go back to our data set of passages and find the next best candidate. So at each step, it incorporates the information that it's retrieved into the new query. So in this example, the idea is you would ask, what is the nickname of Judy Lewis's father? And the best passage, probably, if you just run DPR, is going to be the passage that's specifically on Judy Lewis. So then you would take your original question and this new passage on Judy Lewis, and you would run that against your data set. And in this instance, because we've already found the Judy Lewis article, the next best one it might find, or that we wanted to eventually find, is the article on Clark Gable, because this was included in the passage of the original, and this contains the information that we need. So it's sort of ranking these and combining these to try and account for multi-hop questions. And this model doesn't include the way in which the reader then uses this information. That's sort of separate and specific to the reader. But this is just a way for us to keep generating, and you can go as many steps as you want to keep kind of recursively generating the new best candidate articles from your dense corpus index.
So that,
Nick, this is Miles. This is it's a great explanation. How do you know if you need to go back with and add to, how do you know that you need to do this as opposed to just stopping with what you've got? Is it just the score?
Yeah, it's a great question. It's that's not specified, but that would be a good kind of variation that one would add into their system. So I think in this paper, they essentially set the depth or the number of times we go back to some number, and they try and see if that is better than just a straight DPR. What is the top 50 candidates? We say, what are the top 50 candidates if you try this recursive application? But if you were building your own system, right, a good idea would be to say, well, I've retrieved the top 2 candidates, and their score is kind of below a certain similarity threshold that I like. So let's run the model again and have it keep going. So there's no prescribed way to use this, but like you're suggesting, I think it's a good idea if you were curious and building this kind of system where you'd say, oh, the top similarity result isn't even that similar, so let's keep hitting our data set to try and keep aggregating more information. So kind of along the way in these larger QA systems, if you are really kind of building it very specifically for your application, these kind of ranking ideas and applications and thresholding, these are kind of little components that you add within the layers just to make sure that you're kind of getting the best results.
do you know what the MIPS acronym stands for? Is it like inner product search or something like that?
Yeah, it's maximum inner product search, which is just inner product search and then taking the maximum. This is unhelpfully not explained when you Google it. It's all but yeah. It's its own topic of how do we optimize this kind of computation heavy search. So there's all these quantization ideas about how to do maximum inner product search, but they're just taking it here as vanilla.
Sounds like a synonym for like k nearest neighbor search with cosine similarity.
Yeah, it's a very kind of ornate term for a very intuitive idea.
Yeah. Okay.
Okay, so that's multi-hop, and let's see, I think we've got 2 more here. Realm, and this is a kind of this is an interesting one. I think this diagram does a decent job of summarizing it. If you think back to the pre-training task for BERT or any kind of transformer architecture, we have a closed task, CLOZE, which just is fill in the mask token task, which is how the model kind of wants to generate its embeddings. It's understand language, understand. So traditionally, if you just look at the left column of this diagram, essentially we just ask the model, we paid 20 blank at the Buckingham Palace gift shop. You just feed in a lot of examples, and eventually it starts to kind of hard code this knowledge, and way down the line, it'll understand that pounds is the best, is the highest likelihood word to fill in for that mask token. So in Realm, basically they're asking, I think this is Google, and it's, I think sometime this year, they're asking, how do we augment this by relying on some kind of external database to, we focus on the task to sort of speed this up or make it a little smarter, essentially. So we add this neural retriever component, and its job is to go into a document store and find a couple of the most relevant documents. So in this case, it's come back with Buckingham Palace gift shop, something on the UK, and then it uses that. It sort of appends this to the original sentence and then proceeds as if it's a regular BERT model. So instead of the closed task where we just have, we paid 20 blank at the Buckingham Palace gift shop, it appends to that this extra kind of knowledge that's relevant to the topic, and then it feeds that through the traditional kind of BERT architecture. So it's this kind of intermediate loop step where we augment each of our sentences with more knowledge. And this is nice because it's unsupervised. And as we're feeding back, the neural retriever itself gets trained. Concatenates, the retriever is trained. So essentially the retriever is trained as a byproduct of this larger task. So if it's pulling out documents that are relevant to the question appropriately, then great. There's very little error propagation. If it's pulling out bad ones, then there's more error propagation. And so it's sort of a byproduct, but then we can take that neural retriever and apply it just as its own component to future systems. So essentially, it's like they've trained a transformers model like a BERT, and then they've added in this kind of intermediate loop step, and then they can separate this intermediate loop step of a neural retriever as its own component, and then they can use this in a QA system or any kind of information retrieval task. And I'm curious, I didn't see it in the paper about how this affects this model, whether that model ends up being better or worse because it's relying on a neural retriever. But all in all, it's an interesting idea, and this neural retriever gets very good scores. It's sort of similar to DPR in performance.
So you take out, you do the closed task, which means like randomly masking out some words in the query. Is that right?
Mm-hmm.
And then you do just like DPS neural retrieval to find the closest matches. And then you try to solve the closed task, like fill in the masked terms by feeding in both the retrieved documents and the masked query.
Mm-hmm. Yep.
Okay. Gotcha. And then you can backprop on that whole thing.
Yeah. So it's like at each of these pre-training steps, the closed task just has kind of more evidence stuffed around it. So where in a traditional pre-training task, we pay 20 blank at the Buckingham Palace gift shop. The evidence that the model has to try and figure out what the masked token should be is essentially, the words limited to that sentence, Buckingham Palace, and paid 20. With this, basically, we're just stuffing in more text that we think is relevant. And if it is, it's going to help it's going to help the model predict things a little faster just because it has more evidence.
Okay. And so this illustration is just describing the pre-training process, and then in the end, you just when it's time to actually use it as a retriever, you just take that neural retriever component.
Yeah, exactly.
Okay.
Because this has been trained end to end.
So it's really a way. It's like it's still just a dense neural retriever in the end, but this is a way to train that effectively.
Yes.
Okay. Cool. All right.
Yeah. All right, and the last one I have here is GAR, Generation Augmented Retrieval, and it's similar. I'm really hazy on the details of this. I can't really understand how it works, purely because there's one paper and not much more information, so I'll have to really dig in to figure out what they're doing here. But essentially, the idea is that you can use a DPR or something like that, but before you feed in your question to be encoded, you augment it with additional data. So similar to Realm, you would augment the query with things like if your query was about Clark Gable, then you would feed in relevant passage titles like Clark Gable would be the title of his Wikipedia page, and maybe the surrounding sentences from which the question is most relevant in Wikipedia. I'm very confused about how one gets these. So they talk about adding context to the question before you feed it in, which makes sense. That's good because then your question against the data set is richer and it has kind of more contextual information to help you find the best passages. But that's sort of putting the cart before the horse. I don't really understand. If you can go out and find the relevant passages, why do you need to then, your task is complete, right? Why do you need to add those and then run it through DPR? So I'm unsure if this is like, we used this as a labeled training task. Yeah, it's a little hazy, but it seems to have good success in a lot of it's sort of not its own retrieval method as far as I understand. It's sort of an augmentation to other methods. So there's sort of a question mark on this one that I'll have to read the paper a little more carefully. But a lot of the efficient QA systems utilize this GAR. So I wanted to at least include it and get a better idea. And a lot of the winners of this question answering system competition used a combination of DPR or something like this with GAR. So it's kind of and if you see here, one of their, this is from the GAR paper, by combining GAR and DPR, you get the best results by a little bit.
Do you think it could involve any generative models?
I'm not sure. It seemed like they're purely looking for they're purely extracting text from that would help augment the question when you're trying to match it against a bunch of database of text. So I don't really understand the mechanism or how one does that. But,
right. Okay.
Yeah. So I guess.
So this plot. Yeah, this plot's showing how GAR plus DPR is at the top.
Yeah, we'll figure out exactly what the implementation details are there. But so yeah, these are all or most of the retrieval components that I saw sort of come out in the last year or two, and that were included in kind of top scoring question answering systems. But essentially, what you should take away from this is a flavor of what DPR does, and kind of the ideas that you can use to augment or kind of modify your neural retriever in sort of interesting ways that might match your application, or just kind of ideas that might augment the performance. So there's, within these different retrievers, there's little ideas about if you were building your own, oh, how do I augment this a little just to get slightly better performance? All right, and that's it for retrievers for now.
On the so I know like a couple models that we've talked about a lot are like the haystack framework, and then also RAG. Do either of those support some of these methods? Do they have them kind of like implemented and ready to plug in, or?
Yes, RAG uses it uses DPR. So RAG is sort of an end-to-end system, and it's essentially DPR combined with the reader is BART, which is a variation of BERT, but it just generates text. It's a decoder. So it's basically just DPR plus BART, and that is retrieval augmented generation. And it's an effective system, but it's end-to-end, so both the retriever and the generator get trained as we're feeding things through. And that shows up in Haystack. And it also has BM25. I think it has a couple others. It has Elasticsearch. But in general, the most support you can find is probably for DPR and BM25. Those are kind of, they're implemented in a few places like Hugging Face, or just kind of popular, well-used libraries. So yeah, if you want to use, I think, GAR, I think you would have to, GR, you would have to go to their GitHub.
A little more manual.
Yeah, Realm, MDR, I think both of these. I'm not sure about Realm. It's a Google product, so they might be supporting it. But I think
for DPR, or like, yeah, the basic DPR, are there like pre-trained encoders for that?
yes. Yeah.
Okay.
Oh, that's a good point. So for all of these, I think they release the pre-trained encoder, which is what you want. I think you're able to also, you could certainly train your own, but you would need labeled data, specifically, here's my question, and here's the text from which the answer is contained. So you could train your own DPR. I don't know how expensive that is, but each encoder is 2 layers or something. So it's not like asking someone to train their own BERT. I believe these can be fine-tuned on your task, which is a very nice pro. So you could take pre-trained DPR, and if you're interested in one of these models and trying it out on your own, your best bet is to take the pre-trained DPR and use that. And if you have your own training data, maybe you run a commercial banking software, and you have these kind of question-answer pairs. I think you can fine-tune DPR on this kind of content specific to your domain, so it gets a little better at your application specifically, and that should show you some improvement because you've trained it on your own domain.
Yeah, nice.
Yeah. And I think that's it for retrieval methods. Any questions?
So great discussion. I think I followed along. So if I understand it right, if we have a I- imagine so we're in operation, ask a question, and I try to answer it first by maybe just a simple table method, and it's so no neural net. I get a
Mm,
bad score, and so I'm going to kick it back to to tier two, to the model. Okay, so, and then on the model side, if I've got to go through a couple of different passages to get the answer, we can wrap the best answer back and send it out again. Uh, where I have a question in my mind is, if we want to do some augmentation, and I guess you have the same question. If you want to do some augmenting, I can take the best score from the table that had a bad score and add that to the query. The trouble is if it's a bad score, then I'm sending bad information with the query.
mm.
So, and so I'm just trying to wrap my head around how do I get that augmented data? Like, and I know you said you had the same question, so I guess I don't have an answer. I'm just following it through to the same edge of that cliff before I jump off.
Yeah. Yeah, I don't understand because if you have good data to supply it, then your task should be done already. But yeah,
Yeah,
this is true.
well, unless you're taking it from a different corpus. So if you've taken it, if you've got everything in a table and you're just doing your best, you're not looking for the best answer. You're looking for the best question that matches the question that's being asked.
Mm,
So, so, but you're not actually looking at the passages at that point if you've got a table. So if maybe if you have confidence in your answer, but you just don't like it, okay, then kick it up. What about on the return stream though? So if you don't like what's coming back from BERT, let's say it's a CLS token, um, is there some way to capture that in a way that makes sense here? The I mean, on our side, we just have the reject stream that comes back. So if
mm.
we get a CLS coming back, we don't want to send that back to the user. So we kick it around for a second try by doing the best with the table and then sending that up again, and kind of keep doing it until we don't get CLS. Is uh is, is there does any of this apply on the return stream too, or not really? Once you get your BERT reply, you stop there.
Uh, yeah, in these systems, let me see if I can understand. In these systems, you're essentially trying to come out with encoded vectors, um, but you are matching these encoded vectors with your query, and then the text passage to which this encoded vector corresponds is the kind of thing that you feed back. I'm not quite understanding is this like an escalation process within your own system where if one system does a bad job, then you escalate it to the next system?
Uh, there is that sort of built into the front end of it. The trouble is if what's coming back is a CLS token, which is basically the BERT model throwing up its hand saying, look, if there's an answer here, I'm not going to find it. And so we don't want the user to see that. We want them to see something better, like something that we send to GPT-2 and it comes back and says, oh, it's a sunny day today. I mean, of course, that's irrelevant. But so it's a just maybe it's the way you said it. It's an escalation. So so that if you don't like what's coming back, which is CLS, okay, is there a way to use these methods to fix it up, or does maybe it needs something else, like to kick it out to yet another model? Maybe you've
So
answered my own question.
when you say like returning CLS, so it sounds like you're referring to like using the like the squad like span retrieval
Yes,
with
that's
BERT. Yeah. Okay. And
right.
and the
Whether
span
it's
it's
the
returning is just CLS,
Oh,
which is
I see what you're saying. Oh, okay. Huh. Yeah, that's a good question. Like specifically on the last notebook that we sent, yeah, if it doesn't have a good answer, it sends out the COS token.
and maybe that's the right thing though. You don't want the system just making stuff up.
Yeah,
Well, it depends on the application.
yeah.
But, okay, it's just a thought, just trying to putting myself in the place of the user, and then saying, wait a minute, you say you don't know to any now, so I'll ask it differently, and it's another I don't know because the information isn't there. So
Yeah.
Okay. All right, just a thought. Maybe there's no right answer right now. I appreciate
No,
the
that's
attention to that.
yeah, it's a good idea. If there's you don't want it if it has very low confidence or it's the information is not in this corpus. It's helpful to know that also,
Sure.
rather than it's the user going back and back and back to try and modify their question when in fact the answer is just not contained in the system at all. Yeah.
Okay. All right. Thank you.
That makes sense. Okay, so yeah, the idea is like if at the very end of your search you use BERT to try to extract the answer that you want to give the user, and it comes up with CLS, then you know something's gone wrong. So you could take that information and try to like go back, repeat the process, and do something different. Maybe search deeper, like include, like retrieve more context articles or something like that. Yeah.
Yeah, perhaps, or maybe just kick it up to the tier 3 bot.
Yeah. Yeah. So, and it does sound like that's part of the so yeah, we've been talking about the retriever, but then the reader is next, and like using BERT to extract a span is just one kind of reader approach. But it looks like there's some others.
Yeah, the others can essentially take this question or we'll take the question and or the context of the question, and it generates text. So instead of picking a selection out of the passage it finds, it actually generates novel text that might be able to combine two different pieces of text, or just it's novel text, so it will spit out something. But of course, it could spit out nonsense if there's no relevant.
Yes. Right. Okay, good.
Yeah. Yeah, that's an interesting aspect of this. Like, what do you do? You can tell that it's failed in some way.
That's the good thing about BERT. It knows what it doesn't know. That's a blessing.
Yeah, right. The fact that it returns CLS is sort of a helpful behavior. It's telling you like, I don't know. Versus a lot of these other retrieval methods, they'll spit back whatever the closest match is, even if that kind of sucks.
Right, but it gives you a score, so you can do something with it.
Yeah, that's true. Cool.
Any other questions on, I guess, on anything?
So I see there's some notes in here on reader options, but we're going to save that for another week.
Yeah, that's just sort of aggregating so when I was looking at these competition winners, they used, some of these models. So in a similar format, next time we talk chatbots and AI, we might just go through the different kind of readers and what they do. And then from this, we have a bunch of components built up, and we can figure out which ones to combine to create our end-to-end question answering system.
Cool. Yeah. Would a like interesting next step be to like go back to our first notebook and replace TF-IDF with something like DPR?
Yeah, we could do that. Or just do a RAG, Retrieval Augmented Generation notebook, or any kind of iterative step to make a more advanced, question answering system.
Yeah, so RAG, let's see. Well, RAG specifically uses BERT, right? It's a generative approach. But Haystack is more of like a framework where you can like plug and play different approaches.
Yeah.
So could you, like in Haystack, could you build for instance, like DPR for retrieval and then BERT in span retrieval mode as the reader?
I'm not quite sure in Haystack, but in Hugging Face you could build that. Yeah. So we can mix and match these components. I think certainly in Hugging Face, and then in Haystack, they don't have quite as many models or components, but it's sort of productionized nicely where they've got built-in, very efficient stores and indexing, and so it's sort of built out as a production system.
Yeah. Okay.
Oh, Alejandro's. I've seen the GPT-3 sort of reverse engineered version.
Oh, nice.
Yeah, I haven't looked much at Luther, but I've heard of this kind of project where they're reverse engineering these big models, and I think trying to make them smaller, more manageable. But yeah, it's on my list of things to check out. You can just open that in a tab. Yeah.
Nice. So presumably they have access to GPT-3 and they're running test searches on it or test runs, getting the results and using it to like train a smaller model or something.
Yeah, there's kind of methods like this where people reverse, and there are a few interesting papers where people reverse engineer models at a fraction of the cost. So it's sort of like model hacking. It's very cool. But you could take in theory, you could take someone's proprietary hard-earned model and reverse engineer it by querying it enough.
Yeah, they let you do that cheaply.
Yeah, it's a cool set of projects.
Yeah.
Yeah.
Well, one thing I wanted to do before we sign off here, the Big Bird tutorial is finally ready. So there's an announcement email going out in just a little bit here. Can I take the presenter view from you briefly?
You sure can. There we go.
Yeah. So thank you guys for participating in the discussion group for this. I think that was really helpful. I think both for me, just in terms of like motivating it and helping me get through it, but also like a lot of great feedback. So yeah, what I ended up putting together, I took all the insights from our discussion group, created a sort of a video lecture, broke it down into like 9 little bite-sized chunks, and then I actually wrote an ebook on it first. That kind of helped me organize my thoughts, create the illustrations I wanted, and I know some people prefer that medium, so that's there. And then the notebook that we played with, where we tried to apply Big Bird to like the long test comments from the 20 news groups data set, that's in here too. So yeah, there you go. Check it out. All right. Yeah, so next week, I think we might be doing BERT with categorical features. Nick and I will talk about that next, I guess. We'll figure out what next week will be, but kind of the plan is to weave those two things together. Like Nick and I will maybe switch off weeks or something, doing BERT with categorical features and then continuing this QA discussion. So we'll let you guys know what's next. But thanks everybody for being here. We'll see you next week, hopefully.